In this lesson, you will learn how to use transparent operation mode and layer 2 switching on FortiGate. In this lesson, you will explore the following topics: virtual local area networks, VLANs, transparent operation mode, virtual wire pairing, software switch, spanning tree protocol, STP, best practices. After completing this section, you should be able to configure VLANs to logically divide a layer 2 network into multiple broadcast domains. Describe VLANs and VLAN tagging. By demonstrating competence in understanding and configuring VLANs, you will be able to effectively divide your network into smaller logical segments. VLANs split your physical LAN into multiple logical LANs. In NAT Operation Mode, each VLAN forms a separate broadcast domain. Multiple VLANs can coexist in the same physical interface, provided they have different VLAN IDs. In this way, a physical interface is split into 2 or more logical interfaces. A tag is added to each Ethernet frame to identify the VLAN to which it belongs. This slide shows an Ethernet frame. The frame contains the destination and source MAC addresses, the type, the data payload, and a CRC code to confirm that it is not corrupted. In the case of Ethernet frames with VLAN tagging, according to the 802.1q standard, 4 more bytes are inserted after the MAC addresses. They contain an ID number that identifies the VLAN. An OSI Layer 2 device, such as a switch, can add or remove these tags from Ethernet frames, but it cannot change them. A Layer 3 device, such as a router or a FortiGate, can change the VLAN tag before proceeding to route the packet. In this way, they can route traffic between VLANs. When operating in NAT mode, FortiGate operates as an OSI Layer 3 router in its most basic configuration. In this mode, a VLAN is an interface on the device. VLAN tags may be added on egress, removed on ingress, or rewritten based on a routing decision. FortiGate does not add VLAN tags on ingress. This is the responsibility of a previous device. In this example of NAT Operation Mode, a host on VLAN 100 sends a frame to a host on VLAN 300. Switch A receives the frame on the untagged VLAN 100 interface. After that, it adds the VLAN 100 tag on the tag trunk link between Switch A and FortiGate. FortiGate receives the frame on the VLAN 100 interface. Then, it routes the traffic from VLAN 100 to VLAN 300, rewriting the VLAN ID to VLAN 300 in the process. Switch B receives the frame on the VLAN trunk interface and removes the VLAN tag before forwarding the frame to its destination on the untagged VLAN 300 interface. To create a VLAN using the GUI, click Create New, select Interface, and then, in the Type drop-down list, select VLAN. You must specify the VLAN ID and the physical interface to which the VLAN will be bound. Frames that belong to interfaces of that type are always tagged. On the other hand, frames sent or received by the physical interface segments are never tagged. They belong to what is called the native VLAN, VLAN ID 0. Note: in a multi-VDOM environment, the physical interface and its VLAN sub-interface can be in separate VDOMs. Good job! You now understand VLANs. Next, you'll learn about transparent mode. After completing this section, you should be able to configure FortiGate interfaces to operate as a Layer 2 switch, configure a virtual domain, VDOM, to operate in transparent mode. By demonstrating competence in understanding and configuring transparent operation mode, you will understand a key component of implementing Layer 2 switching on FortiGate. Traditional IPv4 firewalls and NAT mode FortiGate devices handle traffic the same way that routers do. Each interface must be in different subnets, and each subnet forms a different broadcast domain. FortiGate routes IP packets based on the IP header information, overriding the source MAC address. So, if a client sends a packet to a server connected to a different FortiGate interface, the packet will arrive at the server with a FortiGate MAC address instead of the client's MAC address. In transparent operation mode, FortiGate forwards frames without changing the MAC addresses. When the client receives a packet from a server connected to a different FortiGate interface, the frame contains the server's real MAC address. FortiGate doesn't rewrite the MAC header. FortiGate is a layer 2 bridge or switch. So, the interfaces do not have IP addresses, and by default, all belong to the same broadcast domain. This means that you can install a transparent mode FortiGate in a customer network without having to change the customer's IP address plan. Some customers, especially large organizations, don't want to reconfigure thousands of devices to define a new internal network that is separate from their external network. This slide shows an example of NAT Operation Mode. FortiGate has 3 connected ports, each with separate IP subnets. All interfaces on FortiGate have IP addresses, and in this case, NAT translates between networks. Firewall policies allow traffic to flow between networks. FortiGate handles packets according to their routes. In most cases, routes are based on the destination IP address, at layer 3 of the OSI model. Clients on each subnet send frames that are destined for a FortiGate MAC address, not the real MAC address of the server. This slide shows an example of transparent operation mode. Firewall policies scan and allow or block traffic, but there are differences. Notice that the physical interfaces on FortiGate have no IP addresses. Therefore, FortiGate won't respond to ARP requests. However, there are some exceptions. For example, when changing to transparent operation mode, you must specify a management IP address in order to receive connections from your network administrators and send log messages, SNMP traps, alert email, and so on. This IP address is not assigned to a specific interface. It is assigned to the VDOM settings. The management IP address has no effect on traffic passing through FortiGate. By default, a transparent mode FortiGate won't perform NAT. Also, clients will send frames destined directly to the real router or server MAC address. A transparent mode FortiGate acts as a transparent bridge. What does that mean? It means that FortiGate has a MAC address table that contains, among other things, the interface that must be used to reach each MAC address. FortiGate populates this table with information taken from the source MAC address of each frame. FortiGate, as a transparent switch, splits the network into multiple collision domains, reducing the traffic in the network and improving the response time. By default, in transparent operation mode, each VDOM forms a separate forward domain. However, interfaces do not. How does this affect the network? Until you change the initial VDOM configuration, all interfaces, regardless of their VLAN ID, are part of the same broadcast domain. FortiGate will broadcast from every interface in the VDOM in order to find any unknown destination MAC address. On large networks, this could generate massive broadcast traffic and overwhelming replies, a broadcast storm. This slide illustrates a problem. A broadcast with all the interfaces on the forward domain 0 default. One device sends an ARP request. It reaches FortiGate through one of the interfaces in the VDOM. Because all interfaces belong to the same forward domain, FortiGate rebroadcasts to all the other interfaces, even to interfaces that belong to different VLANs. This generates unnecessary traffic. After that, the ARP reply will still arrive on only one interface, and FortiGate will learn that the MAC is on that interface. As you learned earlier in this lesson, forward domains are like broadcast domains. The example on this slide shows the same network as before, but different forward domain IDs are assigned to each VLAN. Traffic arriving on one interface is only broadcast to interfaces that are in the same forward domain ID. Good job! You now understand transparent mode. Next, you'll learn about virtual wire pairing. You can use virtual wire pairing when only two physical interfaces need to be connected to the same broadcast domain. The most frequently seen example of this is FortiGate connected between the internal network and the ISP's router. When you configure virtual wire pairing, two ports are logically bound or linked, acting like a filtered cable or pipe. All the traffic that arrived at one port is forwarded to the other port. This prevents issues related to broadcast storms or MAC address flapping. You can create more than one port pair on FortiGate. This slide shows an example of two virtual wire pairs used on FortiGate in transparent mode. This FortiGate has 4 ports, each connected to different physical locations, but traffic is not allowed to flow between all 4 locations. Virtual wire pairing allows traffic only between ports in the same pair, between port 1 and port 2, and between port 3 and WAN 1. So, in this example, the network on port 3 can reach the internet through WAN 1. However, the networks on port 2 and port 1 can't reach the internet. They can only reach each other. When you create a virtual wire pair, you must select 2 physical interfaces, no more, no less. After selecting the 2 interfaces, you create the virtual wire pair policies that inspect the traffic crossing the virtual wire pair. The wildcard VLAN setting specifies how those policies are applied to the different VLANs whose traffic flows between the pair. If wildcard VLAN is enabled, the virtual wire pair policies are applied equally to the physical interfaces and VLANs. If wildcard VLAN is disabled, the virtual wire pair policies are applied only to the physical interfaces. Traffic with any VLAN tag is denied. The firewall policies for virtual wire pairing are configured under a different menu item. This menu item is displayed when you have created at least one virtual wire pair. Remember that you will need separate firewall policies for traffic flow in each direction on the virtual wire pair. Good job! You now understand virtual wire pairing. Next, you'll learn about the software switch function. After completing this section, you should be able to configure a software switch. A software switch adds a virtual layer 2 switch to the FortiGate configuration. By demonstrating competence in using the software switch feature, you will understand how to group multiple physical and wireless interfaces into a single virtual interface. After completing this section, you should be able to install FortiGate in networks running Spanning Tree Protocol, STP. By demonstrating competence in STP, you will understand how to install FortiGate in a network running STP, and how to avoid common STP-related issues. Whenever possible, network designers try to provide redundancy in their networks. The larger the network, the more critical the need for redundancy. However, redundancy introduces its own issues. When an Ethernet switch receives a frame, it forwards that frame to all ports in the same broadcast domain, except the port it received the frame on. If there is a redundant path in the network, the frame will be broadcast over both links. This would create what is called a broadcast storm, which will eventually lead to a complete collapse of the network as the frame gets rebroadcast over and over again across each port. When you implement a FortiGate device that has Layer 2 features, these are some best practices you should follow to avoid preventable issues within your network. Congratulations! You have completed the lesson. Now, you will review the objectives that you covered in this lesson. This lesson covered the following objectives. Configure VLANs to logically divide a Layer 2 network into multiple broadcast domains. Describe VLANs and VLAN tagging. Configure FortiGate interfaces to operate as a Layer 2 switch. Configure a VDOM to operate in transparent mode. Segment the Layer 2 network into multiple broadcast domains. Configure a software switch. Install FortiGate in networks running STP. Understand best practices for using Layer 2 switching on FortiGate.